Howdy, if you're PreCal, it's Miss Kosh. I am back doing multiple choice problems that were written by Mr. Passwater, so yay, thank you to him. This is the 5th video of Unit 1, and I'm going to skip a bunch of these because they're all pretty similar. The inequalities, they're pretty solid, but I think I did these in video 4, I think it was. And I don't know that I want to get just too bogged down in what's repetitive, so my apologies if you think you need it, but anyway, time is limited. So I do want to jump down to this one here because, so on all of these we were comparing things to 0, which is great and wonderful, but now we're comparing two functions to each other. So there's probably more than one way to do this, but let me show you how I would think through this one. I would begin by trying to figure out when are my two functions equal to each other. So I would set them equal. If I could write out my numbers, that'd be great. So I'll subtract x squared, I'll subtract that, gives me negative 3x, I'll subtract that, gives me negative 10. Oh, this factors nicely, this is good. It's a negative 5 and a positive 2. Okay, and so now on my number line, I have a negative 2 and a positive 5. And so I could look at this and say, okay, well my f of x is equal to, oh, I just forgot. F of x was this one. 2x squared plus x minus 4, and my g of x is equal to, I haven't thought about these problems in a little while, so this may or may not be the most efficient way to do it, but it'll get the job done. Okay, so what I'm going to do is I'm going to figure out, okay, what's f of 0? Maybe I'll write the f of 0 above the line. When I plug in 0, I get negative 4, so let's write it this way, f of 0 equals negative 4. And then g of 0 equals a positive 6. So what were we trying to do? We were trying to figure out when is f less than g. Well, on that interval, f is less than g. Let's double check and just plug in. We'll do f of negative 3 with g of negative 3. I mean, I think that these are both quadratic, so they should they should have some sort of bouncing, or like, I think it's only going to be this interval, but just because I'm in a different headspace currently, this becomes 9, so negative 3 squared is positive 9 times 3 is 18, minus 3 minus 7, well, minus 3 minus 4 is minus 7, so 18 minus 7. Did I do that correctly? Is 11. Okay, then this is a positive 9 and a negative 12, which is a negative 3 plus 6 is now a positive 3. Okay, what did I expect? I expected this one to be less than. Okay, so my reasoning was pretty solid. If I wanted to, I could graph these, but I think that may be the hard way to do this. So from negative 2 to 5 is where f is going to be less than. So I think this is our answer choice here. I would do something almost identical for the next problem, so let's not do that. And 94 looks the same. Okay, so 95 looks a little different, so we'll talk about that one. Here's our polynomial. Which of the following describes the zeros? Okay, so immediately what I see is this is the difference of squares. And so if you don't know that a squared minus b squared is equal to a minus b times a plus b, or you can switch that order, then take a dry erase marker and write this really big on your bathroom mirror so that you see it all the time. This just needs to be second nature for us right here. Okay. Likewise, while I'm thinking about it, if you also don't know that what a plus or minus b squared is equal to, this is a squared plus or minus 2ab plus b squared. If this, you can't just spit this out all the time, also write this, take that same dry erase marker, write it really big on your bathroom mirror so that you see it all the time. This is just a foundational part of mathematics. Okay, that should be quick and easy. You shouldn't have to think about that. Okay, so what I see here is that this can factor down to x minus 3x plus 3. So those are two real roots. And then this one, as soon as I take x squared plus 4 and I set it equal to 0, I get x squared equals negative 4. And so I take square root plus minus. I get 2. If you don't know what I'm talking about, go back and watch my cheer video. Especially from COVID, it's kind of ridiculous. Okay, so My brain stopped. Square root, plus minus. I'm taking the square root of a negative, which gives me 2 non-real zeros. So my zeros here are plus or minus 2i and plus or minus 3. But they weren't really asking for all that. I just gave it to you. So it has 2 distinct real zeros and nope, it has 2 non-real. It has exact 3, nope. Keep in mind, if you've got 2, if you FOILed this out, you would get x to the 4th power. And they end up all being the same, but okay. So it's 4 distinct real, nope. Has exactly 2 distinct real and 2 non-real. Yep. There we go, that was fun. Okay, so which one, what would we do here? On this one, we know, okay, this is gonna give us a real root here. We're gonna have 2 roots from this one, so let's just see. We can use negative b plus or minus the square root of b squared minus 4ac all over 2a. We can use this part right here as what's known as a discriminant. We can use that to tell us what kind of roots they're going to be. So if I have b squared, that's 9 minus 4 times a times c. This is all positive, so this is going to give me 2 more real roots. So I'm going to have 3 real roots, 3 distinct real roots, and that's the correct answer there. There are other ways to do it. I could figure out what the real roots were, but I didn't really care. Oh, actually, oh, you know what? Oh, it almost got me. Okay, check this out. This x minus 3 minus 4 factors down to x minus 4 times x plus 1. And we already had this x plus 1 out front, so we actually have a repeated root. So those are not distinct. It has 2 distinct real roots. That was clever. Good job, Mr. Passwater. Okay, so it does have 3. In IB, we make a distinction about this. We talk about repeated roots versus non-repeated roots or distinct roots and that sort of stuff. So there are 3 real roots. They're just not 3 distinct real roots. There's 2 distinct real roots, and one of the roots has a multiplicity of 2, which we've talked about in PreCal 2. Okay, I think, oh, you know what? This one, he's not gonna catch me again. This x minus 3, this factors down to x minus 3 squared. Because this is, what did we just write down a minute ago? This is that pattern. So if you know this, then you can see this and get there really quick. So this only has 1 root. Basically, g of x right here is equal to x minus 3 cubed. So it has 1 distinct real root that has a multiplicity of 3. 2, 3, 1 distinct real root, and no non-real zeros. I would agree with that, because it was 1 real root with a multiplicity of 3. Okay, let's move on to another page. The table gives a polynomial function. How am I doing on time? Okay. It gives a polynomial function g at selected values of x. What is the least possible degree? Oh, okay. What would I do with this one? I would say, well, this from here to here is minus 2. This is minus 2. This is minus 1. This is plus 1. So it's not linear. Did I do that correctly? I think I did. Okay, and then what did I do to go from here to here? I added 0. What did I do to go from here to here? I added 1. What did I do to go from here to here? I added 2. Okay, so it's not linear. It's not quadratic, but notice this is plus 1. This is plus 1. It could be cubic. So what is the least possible degree? Well, it's not this. It's not this. So I would say that's the least possible degree. It's not a bad idea to check my answers against the answer key. But I'm not going to do that currently. This one, same idea. These all add up. We're adding the same thing each time, which is great. What did I do? I added 0, I added 1, I added 2, I added 3. That's not linear, but I do add 1, add 1, add 1. So that's quadratic, which means its least possible degree is degree 2. You know what? That's repetitive. So, I mean, it's great. It's good practice, but I'm not going to do it all for you. Okay, let's see. What's happening here? This one we added, so these are all, notice I am checking on all of these that this is a constant rate of change, because if it's not, it changes. We're looking at the ratio, but when this is plus 1 the whole way down, life gets easier. If it's plus 3 the whole way down like this, we're fine. That wasn't very clear, but okay, plus 5, plus 3, plus 1, minus 1. So what did I do? I subtracted 2, I subtracted 2, I subtracted 2. So this is quadratic, so let's see which of these. So it's not linear, it's not linear. It's best modeled by a quadratic function because the average rate of change over any length interval are constant. Average length change? No. This was the average length of change. Okay, so it's because successive second differences of the output over the equal are constant. Yes, I think that's the correct answer. I think the next one is very similar. We're going to skip it. Oh, here's an imaginary number. What is the least possible degree? So I see that it's got a real polynomial function p. 0 of p is this. What is the least possible degree of p? Well, I see one real root right here. So that's going to give us, it passes through, so it has a multiplicity of 1. Not a value of 1, but a multiplicity of 1. This one is bouncing, so it has an even multiplicity. So let's assume what is the least. So we'll assume that it's got a degree of 2. Here's where I would get a little particular. I would say, I would have written the question to say, shows the graph of a polynomial function, I would say with integer coefficients. No, I would say with real coefficients. And then that means, okay, so here's what I'm talking about. If I can take the polynomial, or I can take the zeros, x minus 1 and x minus 2i, okay? And I can FOIL this out, and I get x squared is my first term, and then I have a minus 2ix and a minus 1. So this is like minus, and then it's 1 plus 2i that's getting multiplied by x. Did you see how I did that? And then this becomes a plus 2i. And so this is quadratic, but it doesn't, and this guy, so we often think that the imaginary parts travel with their conjugate. I like to say they travel with the buddy. But they don't have to, but when they don't travel with the buddy, you're going to have coefficients, like here your a value is 1, your b value is technically a negative 1 minus 2i, excuse me, and your c value is 2i. But when we have, in order for all these coefficients to be real, this complex root is going to have to travel with its conjugate, travel with a buddy. Okay, so what I would have done had I written this problem is I would have said the polynomial function p with real coefficients. Okay, because you can allow for the situation where the coefficients are non-real and then he's just by himself. But if they're real coefficients, then 2 plus 3i would also be a 0. That's the conjugate. So therefore we had, well, let's assume we usually write problems where we're assuming that they're coefficients. These are just nasty to work with. We don't tend to do that. So we have 2 roots here. We have 1 root here that puts us at 3. We have 2 more here that puts us at 5. I would imagine the answer is 5, but if I had written that question, I would have tweaked it a tiny bit. Okay, the function, what's the end behavior? Oh, good. So what do I see? I see that it's cubic with a positive leading coefficient, so that means it's going to do something like that. So as x goes to negative infinity, y goes to negative infinity, which is good, so that means we can cross out those two. As x goes to positive infinity, right here, nope, we go to positive infinity. So that would be C, assuming that I can see what I'm doing. Okay, the next one is very similar. And, oh, all these limit problems, they're great. Let's look at this one because it looks a little bit more interesting. What I notice is if I FOIL this all out, I'm going to have a negative leading coefficient, and it's degree 5. So negative leading coefficient with degree 5 means, okay, that's not what happens. But ultimately, they go in opposite directions, and negative means that we end up going in the negative direction. So as we go to the negative, we end up positive, so not this one or this one. As we go to the positive, we end up positive. Nope, we end up negative. So that would be D. Okay, let's see. Which of the following, the sign of the leading term P is positive, the degree of the leading term is odd. Okay, I agree with both of those things. So therefore, odd and positive means that as we go to negative infinity, we go to negative infinity. So odd and positive does something like that ultimately. And so not this one. Negative, negative, positive. Nope, it should be negative, negative, positive, positive. So negative, negative, positive, positive. I think it's this, but are these words the same? Yes, okay. Anyway, that was fun. End behavior, more end behavior. Oh, okay, let's look at this one and then I'll stop the video here. And we'll pick up again in a minute. Okay, so on this one, what is it telling us? As I go to negative infinity, I'm going to positive infinity. So I'm going to come from up here. And then as I go to positive infinity with the x, my y is going down. So I'm doing something like this, which tells me it's an odd degree with a negative leading coefficient. Odd degree with a positive leading coefficient, no good. Even degree, no good. Odd degree, negative, yep. Even degree, negative, nope. There we go. Okay, come back for more videos. I will keep going. Subscribe, do all the things. Let me know how I can help you. I'm doing the best I can to get as many people ready for this AP exam. So let me know how I can support you and be patient with me. All right, goodbye.